Hey everybody, this is Mr. Brooks again. So today we're going to start into the next section after test 3, which is dealing with power series, and what a power series actually is what we're going to get into for 11.8. And then we're going to get uh, into series that are going to represent the function, or a function that's going to represent a particular power series, which is really neat. There is a lot that's in 11.8 or 11.9 when that happens. And then we get into what we call McLaurin and Taylor series. And those guys, a lot of people freak out about them, but they're really not that bad, especially when you get into the things about it. But this is going to start off our power series section. So having a good knowledge of your basic convergence and divergence tests that we have, like the test for divergence, the ratio test, the root test, geometric series, P series, all of those guys are going to be highly important for these sections. So this is why I've split this up to dealing with what's the basic necessities for series, and then this is kind of an application section when we get into there, and being able to come up with functions using series as well. So first of all, a power series power series is of the form the summation as n goes from 0 to infinity. And again, we've seen where this index, this n is equal to 0, it can change for that. And so depending on where we're at, we can shift that around. But most of the time we will start at 0. And we'll have c sub n x to the n. All right, so this is going to look like c sub 0 plus c1 x to the first plus c2 x squared. And it's going to continue this pattern for infinity. So here, notice that we're using x now instead of a sub n or anything like that. Here, x is a variable, okay? And so it can be any fixed value that we choose. And the c sub n's, those coefficients out front, are constant values. So constants are, and so we'll treat these guys as coefficients. So they can be any real number for that case. So of the series. So important note here is for each fixed value, or each value of x, we can discuss the convergence or divergence of a particular series. And one important note here is that the sum of the series is f of x, so notice that it's a function here, that is equal to c sub 0 plus c1 x plus c2 x squared plus c3 x cubed plus so on. And here, just to show that it's continuing on out to infinity, I'm going to say c sub n x to the n and so forth, whose domain is the set of all x for which the series converges. Again, because it doesn't make sense to talk about the sum of a series if we have a divergent series. So this is only talking about where this guy is going to converge. Okay. So for example, if we let c sub n, so this is saying all values of n, then the power series becomes the geometric series. Because if we look at it, if c sub n, this formula of the constant coefficients for this guy, are all equal to 1, then that means our summation now becomes from n to infinity of just x to the n, which is 1 plus x squared plus so forth. And we know by properties of geometric series, where do these guys converge? So again, more general. So by now, we know a geometric series converges when x is between -1 and 1 and diverges elsewhere. So we can say when the absolute value of x is greater than or equal to 1. More generally, a series of the form, the summation, as n goes from 0 to infinity, of c sub n, x minus a to the n. So this is going to look like c sub 0 plus c sub 1 times x minus a plus c sub 2, x minus a, the quantity squared, and so forth. This is called a power series. So this is going to have a couple different names. So this is called a power series in x minus a, or a power series centered at a, which is the one we'll probably more than likely go with for terminology's sake. Or an easier way to say this is a power series about a. So what this is saying is we're centering where this power series is located. And that's going to make more sense later down the road. But one interesting fact about here is we will always know if this series converges at a particular value. And in fact, a power series always converges when x is equal to a. Because think about it, if I plug in x is equal to a into this equation, I'm going to get 0 out. And so a series of the summation of 0, that's going to be 0. So we know that it converges. So the big question is where else do these guys converge? So we know that they're going to converge at their center. Do they converge anywhere else? And so that's what the next part of this whole section is about power series, is where are these guys going to converge at? All right, so that leads us into our first example. So take a second, pause the video, and see what you can come up with. Find out where this series converges. Okay, now looking at this, we have x, so we have n factorial x to the n. So knowing that x is some fixed value, what would be an appropriate test that we could use? So something that you should see real quickly that you should be looking at is this n factorial. That's going to tell me I'm probably going to use the ratio test. So let's look at the ratio test real quick. All right, so I'm going to take the limit as n approaches infinity, the absolute value of a sub n plus 1. So wherever I see n, I'm going to replace it with n plus 1 factorial, x to the n plus 1, all divided by a sub n, which is n factorial, x to the n. All right, so we know with factorials, the preceding factorial is built into it. So if we had 5 factorial, so example, real quick, if I had 5 factorial divided by 6 factorial, 6 factorial is 6 times 5 factorial, which we can cancel these guys out and leave us with 1/6. Same thing here. This n plus 1 has n factorial built into it, and we've talked about this before. So I'm going to get just n plus 1 up on top, because n factorial is going to cancel out from the denominator and the numerator. The next piece is I have this x times x to the n, and x to the n here because we had x to the n plus 1. So I'm just splitting this up just a little bit. And now we can cancel some things out. So the n factorials are going to cancel, these x to the n's are going to cancel. And the only thing that we have next is just this limit as n approaches infinity. Let me fix that a little bit. Of the absolute value of n plus 1. And let me fix that. times x. Well, one thing I can do with this absolute value is I could say, well, this is the limit as n approaches infinity of the absolute value of x times n plus 1. The reason I'm able to do that is we know the values of n are approaching positive infinity, so this is going to always be positive. X, however, is some fixed value. It can be positive, it can be negative, so the absolute value is necessary. However, since x is treated here as a constant, especially since we're looking at n approaches infinity, this n plus 1 is going to blow up. So this is going to go to infinity. All right. So let's talk about that a little bit more. Is this always going to go to infinity? Well, by the ratio test, the series would diverge or diverges when x is not equal to 0. All right? Because if x is any positive or negative number, this is going to be infinity is going to be multiplied by some value, so it's still going to be infinity. All right. The only time that this is actually going to work is if x is equal to 0, and before we apply this limit, this all goes to 0. So therefore, it only converges at x is equal to 0. Now, how do I know that? Well, if we look back at this expression here, this is x minus 0 to the n, or just x to the n. And we just stated that this center here, centered at a is equal to 0. Since it's centered at 0, that means it's going to converge at that value. So this is what we're talking about. So now we can say, okay, well, for what values of x can these other series converge? So that's what this next example is on. All right. So we have x minus 3 to the n divided by n. So we want to know for what values this converges. Well, I have an exponential function of some sort with a base of x minus 3. And then I have a polynomial down here. So ratio test is probably still a good one to use. And in fact, this is hinting at what we're going to be doing for the rest of this section, is using the ratio test to help us out with these ideas of convergence. For the most part. Again, we've seen where in the previous chapters where the ratio test becomes inconclusive. And so we've got to be careful of that. But since we're dealing with an exponential function here, we're going to be okay. All right. So, the ratio test. All right. So we're going to take the limit as n approaches infinity of the absolute value of x minus 3 to the n plus 1 divided by n plus 1 times the reciprocal of a sub n, so n divided by x minus 3 to the n. All right, let's see what some values cancel out or what we can combine together. Well, we're going to cancel out these terms here, and these guys are raised to the same power. So I'm going to rewrite just a little bit. So times x minus 3, absolute value. So we can divide by the largest power of n in the denominator and get the limit as n approaches infinity of the absolute value of 1 divided by 1 plus 1 over n, and then multiply by x minus 3. Okay? So, if we apply that limit, another way I could do this x minus 3 is not being affected by n approaches infinity. In fact, this is some constant value because we're saying x is a fixed number. So I'm going to bring out the absolute value of x minus 3 and still look at the limit as n approaches infinity of 1 over 1 plus 1 over n. Well, as n approaches infinity, this is going to go to 1. So all we're left with is x minus 3. All right. So what does this mean? Well, we need this value for the ratio test to do what? in order to converge. So think about what are the conditions for the ratio test to converge. All right. So I'm going to start it out here. So by the ratio test, the series converges when, or is absolutely convergent when the absolute value of x minus 3 is less than 1. That's our conclusions from the ratio test. And divergent when absolute value of x minus 3 is greater than 1. Okay, so let's talk about that real quick. There's one value that we're leaving off here, so we need to worry about that here in just a second. So we know if we simplify this out, so let's look at that real quick. So absolute value of x minus 3 is less than 1 can be rewritten by dropping the absolute value and setting up the following inequality. All right, I'm going to add by 3 all the way through. So if I add 3 through the whole way through, I'm going to get 2 is less than x, which is less than 4. So we know it converges at 2 and 4, and we know it diverges when x is greater than 2, is less than 2, or when x is greater than 4. Okay. But what about x is equal to 2 and 4? Well, we're going to have to look at these a little bit differently, because if we allowed equality here, remember the ratio test states that on the third condition that when it's equal to 1, it's inconclusive. So that means we're going to have to use different tests. So for this, for our first one, when x is equal to 4, we get the series as n approaches 1 to infinity of x minus 3. Well, x is 4, so we're going to get 1 to the n, so that's just 1, divided by n. Well, this is the harmonic series. Harmonic series. All right. When x is equal to 2, this is the series as n goes from 1 to infinity of negative 1 to the n over n. Well, we know, since this is one of our named ones, this converges because it's the alternating harmonic series. All right. And so you would use the AST to prove this. Right? So that means that this following power series converges when 2 is less than or equal to x, which is strictly less than 4. All right. So what does this interval actually mean? So this is where we're going to get into having the correct terminology when we're talking about these. All right. So this is where we're going to get into the radius of convergence and interval of convergence. So this is a big theorem that we have. So for a given power series of the form as n goes from 0 to infinity, now again we just saw that n can start at 1, that's fine. C sub n, x minus a all raised to the n. All right, so we're centered at a. Precisely one of the following is true. Number 1, and we've seen this one already, the series only converges when x is equal to a. Number 2, the series converges for all x So for any choice of x, we get convergence. And the last one, this one's a little bit more convoluted, but this is what we just saw actually. There is a positive number r such that the series converges if x minus a is less than r and diverges if x minus a is greater than r. Now notice that strict inequality here, so we're going to reserve that for a second, but here r is just some positive number that we're talking about. Here, r is called the radius of convergence. Meaning, how big from our center to the left or to the right are we going to have a convergent series? That's all this means. So think of radius of a circle. We're lining up on the x-axis where this is going to converge, starting from a center of A and moving out to the left r units and moving to the right r units. Okay. The interval of convergence, also known as the IOC, and we use ROC to talk about the radius of convergence, so ROC and IOC. All right. The interval of convergence is the interval of all x values for which the series converges. All right. So if we go back real quick and look at what we just did with our work here, the power series converges from 2 to 4. This is our interval of convergence. Okay. Our radius of convergence is when x, okay, when x minus a is less than some value. So our radius of convergence is 1 for this particular case. Okay? And that's because we want for the ratio test the value to be less than 1. Okay? And again, notice the format. It's x minus a. So if we had a 3x minus a, then we would have to divide through by 3. So we're going to see some examples of that here in just a second. All right. And again, interval of convergence can only be found by working through all values of x. So this is where the ratio test really comes in handy because we get to set up this absolute value is less than a number. So that gives us an interval that we can look at. That's what we call, in some books and some lectures, it's called the potential interval of convergence. And then once we investigate what happens at the endpoints, then we could say this is interval convergence, or we can adjust. All right. And so I kind of gave away what we're going to be talking about here in just a second, but I'm fine with that. All right. So again, the interval of convergence is you take x minus a is less than r, and then we make this become a minus r is less than x, which is less than a plus r. So it's finding out what happens with these inequalities here. Do they remain strict, or do we have equality happen at those endpoints? So here, when x is an endpoint, the series could, and so this is talking about the conditions where it could happen, the series could converge at one or both endpoints, or diverge at one or both endpoints. Well, that's a does statement. Yes, the endpoints either are going to converge or they're going to diverge. One of the two. So let's look at something a little bit to help solidify this argument. So for example, if we look at the interval from, the index going from 1 to infinity of x to the n. All right, this is a geometric series. Well, we know a geometric series is going to converge. So we'll call this a geometric power series, if you will. Will converge on the interval of convergence from -1 to 1 because we know the properties of geometric series. So this is what we're using for this. So this would be our IOC. And in fact, for this particular one, the radius of convergence, the ROC, is equal to 1 in this case. And notice the center for this guy, the center, is 0. Okay, so notice here everything lines up. Our interval of convergence centered at 0 and goes out a distance of 1 to either side of 0, so our radius of convergence is incorporated in there. So in general, the ratio test is what we're going to be using. So the ratio test should be used to determine the interval of convergence. And in fact, I'm going to switch that around. The radius of convergence. Again, if you want to use the shorthand ROC, that's perfectly fine. And interval of convergence, except at the endpoints. Again, this is where I said that we will need to have a more intimate knowledge of your different tests that you have, because the ratio test is only going to give you the potential interval of convergence. Then you're probably going to have to use either limit comparison test, direct comparison test, properties of p-series or geometric series or something of that nature to talk about convergence at the endpoints. Okay, so that's where we're at now. So that's all this is. So moving on. Find the radius of convergence and interval of convergence of the following series. So I gave you something a little bit more interesting to deal with. So take a minute, pause the video, and work this guy out. All right. So find the radius of convergence and find the interval of convergence of -3 to the n, x to the n, and the square root of n plus 1. Okay? So I'm going to use the ratio test. And the ratio test is actually going to lead us into finding what the radius of convergence is. That's the nice thing. Right off the bat, it's going to tell us. Now, we do have to be careful when we're dealing with this, but I'm going to demonstrate here what I mean by that. All right, so first of all, we're going to take our limit as n approaches infinity, the absolute value. And technically, I could rewrite this, so I'm going to do this real quick before we start, is -1 to the n, 3 to the n, x to the n, all divided by the square root of n plus 1. So if we wanted to, we could take that out, that -1, because when we take the absolute value of it, we're going to be okay. Nothing's going to happen. The absolute value is going to take care of that, but you've got to be careful when you are dealing with that piece. All right, so we're going to have, and if you do, I'm going to show you what happens if you do leave it in there, so I'm going to do that first. So -3 to the n plus 1, x to the n plus 1, all divided by the square root of n plus 2, because I add 1 to n, times the reciprocal of the square root of n plus 1, divided by -3 to the n, x to the n. All right, looking at our terms, I see an x to the n is going to cancel from both top and bottom. The -3 to the n is going to cancel out. And then we're going to have this big radical here that's going to pop up. So I'm going to get the limit as n approaches infinity of the absolute value. All right. Well, there's only the -3 and x that's going to be there, multiplied by the square root of n plus 1 divided by n plus 2. All right, here I just combined the radical because they were to the same exponent for both top and bottom, so I wrote it as one big exponent for that, which is to the 1/2 power. Nice thing here is applying some basic algebra techniques. We're going to get the absolute value of negative 3x times the square root of 1 plus 1 over n divided by 1 plus 2 over n. All right, again, this negative 3x, that's a constant multiple, but I need to make sure that I keep it in absolute value. And then here, and then I'm going to get the square root of 1 plus 1 over n divided by 1 plus 2 over n. In fact, I could actually drop the absolute value now because I know I'm not going to go get 0 here. So I'm going to go ahead and do that. Well, as n approaches infinity, I'm going to get the square root of 1. So in the end, I get the absolute value of negative 3x. All right. Well, this particular series converges when negative 3x is less than 1, and diverges when the absolute value of negative 3x is greater than 1. All right. So another way to write that is thus the absolute value of negative 3x has to be less than 1. However, this is not our radius of convergence. So what we need to do is first I'm going to pull that 3 out with the absolute value. So that means that I'm going to get the absolute value of negative is positive. This is less than 1. Then this is x is less than 1/3. Notice here we have our format because we said the radius of convergence is of the form absolute value of x minus a is less than r. Okay, so notice here that there now is no value multiplying 3. So this we have to have a coefficient of 1 in front of that x. So that's what we got to be careful of. All right, so here our radius of convergence is equal to 1/3. All right, so now we need to figure out, well, what is the interval of convergence? All right, the potential, and the reason I say potential here is because it could be this. So I'm not excluding this piece out. We know the potential interval of convergence is negative 1/3 to 1/3. And again, this is coming from the absolute value of x. So where this is coming from, absolute value of x is less than 1/3. We get negative 1/3 is less than x, which is less than 1/3. So that's where this is coming from. Okay. So I'm just showing you where this potential interval of convergence comes from. All right. What about when x is equal to negative 1/3 and x is equal to positive 1/3? All right. So we need to check these guys out. So you always check the endpoints unless you're dealing with a geometric series. Okay. So if x is equal to negative 1/3, then we get the summation as n goes from 0 to infinity of negative 3 to the n times negative 1/3 to the n, because we plugged in x is equal to negative 1/3, all over the square root of n plus 1. Well, this is equal to the series as n goes from 0 to infinity. Well, the negatives are going to cancel each other out. The 3's are going to cancel each other out, and we're left with 1 over the square root of n plus 1. All right. We need to see if this series converges. So I'm going to use the limit comparison test. So this is similar 2. The series then goes from 0 to infinity of 1 over, and we're going to move this just a little bit, just to help ourselves out. I'm going to say that this goes from 1 of square root of n, or this is a p series. And this is why I switched my beginning piece here, of n to the 1/2 power. All right. Well, n to the 1/2 power, this needs to be rewrote a little bit more as n to the negative 1/2 power. So here, p is less than 1, which is less than 1. So the series, so this series diverges. All right. I'm going to use the limit comparison test to test out if this one diverges or not. So as n approaches infinity, of 1 over the square root of n plus 1 times the reciprocal of this guy, which is the square root of n over 1. So its limit as n approaches infinity of the square root of n over n plus 1, which we know that this is going to equal 1. Therefore, the summation as n goes from 0 to infinity of 1 over the square root of n plus 1 diverges by the limit comparison test. So notice here I am giving credit where credit is due. So this is what makes these problems a little bit longer. All right, so that we've got that one out of the way. If x is equal to positive 1/3, then the summation as n goes from 0 to infinity of negative 3 to the n times 1/3 to the n over the square root of n plus 1. Well, this is equal to the series as n goes from 0 to infinity. Well, the 3's are going to cancel each other out, and then we have this negative 1 to the n over the square root of n plus 1. Notice that we have an alternating series. All right, so number 1 is the limit as n approaches infinity of 1 over the square root of n plus 1 equal to 0. The answer is yes. Number 2, we have the limit, not the limit, we have is b sub n plus 1 less than or equal to b sub n. So is it decreasing? Okay. Well, you have 1 over the square root of n plus 2 is less than or equal to 1 over the square root of n plus 1. All right, so notice here, this implies that the square root of n plus 2 is greater than or equal to the square root of n plus 1, which this is a true statement for all values of n. So therefore, by the alternating series test, the series converges. Thus, and we'll write this on this next piece here. Thus, the IOC, the interval of convergence, is negative 1/3 to 1/3. Here we have open where it was divergent at the endpoint negative 1/3, and we have a closed bracket here to represent that this is convergent at this. All right, so this is the process when you're going through these problems. So ratio test. Once you do the ratio test, you find out what your radius of convergence is, provided that your coefficient in front of the x is 1. So again, it's of the form absolute value of x minus a is less than r, r being the radius of convergence. Once you have it in that format, then you set up your interval of convergence or your potential interval of convergence and test the endpoints. All right. So find the radius of convergence and interval of convergence for the following series. So again, take a second, pause the video, and try this guy out. All right, I'm going to take the limit as n approaches infinity, the absolute value of -1 to the n plus 1, x to the 2n plus 3. All right, so think about that for a second. I'm plugging in n plus 1, so I have 2n plus 1 plus 1. Well, this is going to give us 2n plus 2 plus 1. So this is where this guy's coming from. Divided by, okay, same thing that's going to happen here, 2n plus 3 factorial multiplied by the reciprocal of 2n plus 1 factorial divided by -1 to the n, x to the 2n plus 1. All right, so this comes to the fun part. So there is a lot of things going on here. Remember, the preceding value is always in the next factorial. So again, 6 factorial contains 5 factorial. It's 6 times 5 factorial. Which also contains 4 factorial, because then you'll have 6 times 5 times 4 factorial is equal to 6 factorial. All right, so for us, just to kind of work to the side, 2n plus 3 factorial is equal to 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. All right, so knowing that, we're able to cancel out a lot of things here. Okay, so I'm going to cancel this x to the 2n plus 1, leaving me with a factor of 2 here. This 2n plus 1 factorial is going to cancel part of this out, okay, leaving me with 2n plus 2 multiplied by 2n plus 3. And then we're going to cancel out a -1 to the n, leaving me the following. So I did cancel a lot of stuff out, so go back through and watch that one more time. All right, I'm left with a -1 x squared, and on the bottom I have 2n plus 2 and 2n plus 3. All right, so I'm going to box this off. That being said, I'm going to bring this out in front. Absolute value of -1 or negative x squared times the limit as n approaches infinity of the absolute value of 1 over 2n plus 2 times 2n plus 3. Well, as n approaches infinity, this goes to 0, which means this whole thing is equal to 0. Well, what the heck does that mean? Well, that means for any value of x, any fixed value, the limit is in fact 0. Well, if that's the case, that means any x value works. So therefore, thus, the radius of convergence is infinity, and the IOC, well, if the radius of convergence is infinity, the IOC is -1 or negative infinity to infinity. So if you do get 0 out, that's a lot of cool things happen. We get that the interval of convergence is negative infinity to infinity, and its radius of convergence is equal to infinity as well. That's the only time that this happens. All right. One more problem to knock this guy out. Take a second and go through this problem, work it out on your own, and then replay the video. All right. So we're going to take the ratio test. You're going to take the limit as n approaches infinity of the absolute value of 3x minus 2 to the n plus 1 divided by 3 times x minus 2 to the n. All right, seeing things cancel out, we're going to get the 3's are going to cancel. We're going to get all copies of x minus 2 except for 1 cancel out from the top. So we have the absolute value of x minus 2, and that's all we have. Well, since there's no n in here, we get the absolute value of x minus 2 as our limit. Well, that means we want this to be less than 1 in order to converge. And notice here, we're in our format of x minus a. So the radius of convergence is r is equal to 1. And then we have the potential IOC is absolute value of x minus 2 is less than 1, and so we're going to work this guy out. So we're going to get negative 1 is less than x minus 2, which is less than 1. Adding 2 all the way through, we're going to get 1 is less than x, which is less than 3. All right, one thing I want to point out before we say we're done is notice what we have here. This is in a geometric series, right? We have our x minus a, we have our c value, so we already know what that this is going to be convergent only at in this side, this interval, so at the strict inequality. And again, the IOC is from 1 to 3. All right, I'm going to show this though. I'm going to prove that this is true, and I've proved so by properties of geoseries. But I'm going to show you why it is here in a second. So again, work to the side just to show. Since we already had it in a geometric series, I can already use this. So here, we say x is equal to 1. All right, that means we're going to get the series as n goes from 0 to infinity of 3 times negative 1 to the n. All right. Well, this is an alternating series. But the neat thing here is its limit as n approaches infinity of 3 is equal to 3. So by the test for divergence, the series diverges. Likewise, when x is equal to 3, get the series as n goes from 0 to infinity of 1, or of just 3, which is divergent. So by the test for divergence, the series diverges. So this is an example of, yes, you could prove that this is true using different tests, but because it was a geometric series, then we could just use the properties. In fact, we didn't even have to use the ratio test to give us the radius of convergence as 1, because we already said that x minus a is less than 1 for geoseries. All right, so you can use this property later on to help you out. If you find out that you have a geometric series, then you can use this property. All right, so that's going to finish us up for today. This is the introduction to power series. So the next thing that we're going to do is represent functions as power series and how this is going to help us out. And this is the reason that we're going for this approach is, remember back when we were talking about integration, and I said that there are some things that we know how to integrate, and we have a lot of different techniques that we have, like partial fractions. We have improper integrals that we could deal with. we have trig substitution, U substitution, all those fun things that we have out there. But there's things out there that we don't know how to integrate. And for example, one of the most easiest functions that we could look at, well, not easiest functions, but a function that we don't know how to integrate that comes up quite a bit is e to the x squared. That base function pops up a lot in statistics, but there's no way that we know how to integrate that. That's where section 11.9 is going to come into play, because we can represent that as a series. And if we know that that series converges, there's a lot of things that we can do with it. So there is a big benefit. So this is leading us to things that we can actually, an extension of integration is what we're going to be looking at in the long run. And so that's why 11.8 through 11.11 are so important, because they can help us with integrating things that we might not have been able to integrate in the past, which is really cool. All right, so that's again the build up for what we're going to be looking at, and I'll see you in the next lecture.